Okay, so we're into the lecture slides part 3. So this is the third PowerPoint on logistic regression. And we're going to talk about practical issues with classification. Remember, logistic regression is about classification, where the general classification problem involves taking a set of features, which we typically denote by the variable x, and using the features for an item to predict whether or not that item is in a particular class. Now, sometimes we will use features to create other features. For instance, in our discussion of overfitting and underfitting, we looked at a model where we had feature x1 and we created a feature x1 squared. And we had a feature x2 and created a feature x2 squared. These additional features can potentially help with the separation into classes. So the question becomes, what additional features should I create? If I have a feature x1, should I use x1 squared, x1 cubed, x1 to the fourth? If I have features x1 and x2, should I use the feature x1 times x2? So we'll address this question in this video. And I do want to point out that this discussion applies not just to logistic regression, but to any classification scheme that could use powers of a feature as additional features. So here's an outline. First, we'll introduce the problem. Then we'll talk about polynomial degree, what polynomial degree to choose. We'll talk about regularization and training set size in the next video. In this video, we'll focus on polynomial fitting. All right, so in the previous part, we discovered that the degree of a polynomial can affect accuracy. If the degree is too low, the model will have high bias. If the degree is too high, the model will have high variance. So this is a linear model. Obviously, it's not fitting the curve trend of the data. This is a polynomial model of degree 4, and it's obviously too wiggly. It's picking up trends that are not really there. So how do we get the golden mean? All right. So too low, high bias, too high, too wiggly. Right. So we want to get the happy mean between minimizing bias and reducing the wiggliness or overfitting. Notice this difference also between underfitting and overfitting. When you underfit, the model doesn't fit either the train or the test data well. If you overfit, the model fits the train data very well, but it doesn't fit the test data well. But the test data is what we're really interested in, because we're interested in how well the model performs on new data and not on the data we used to train the model. Now, we had similar issues when we were considering regularization with the parameter lambda. Remember, the purpose of lambda was to control the size of the model coefficients. The larger lambda was, the more penalty there was for large coefficients. And we had the same issues. If you set lambda too high, then all the model coefficients will become close to 0, and the model will not perform well. If you set lambda too low, you don't effectively do any regularization. Right? So, two separate questions here. In the case where you have polynomial features, how do you choose the best polynomial degree? That's the question here. Right? So how do we find this happy medium where we take the quadratic model? How are we going to identify that? And the second question is how much to regularize. And we won't talk about that in this video, but that is a related question. So all these issues have to do with diagnosing bias versus variance, or wiggliness, what I prefer to call it. And the way you diagnose these issues is to use cross-validation. So we'll see how that works in the next few slides. Another question we'll look at later is how much data you should train on. obtaining data usually is a problem. So you would like to be able to use the least amount of data that you can. But you would think that more data should usually improve your fit. But the question is more data always better, or is there a limit to how much data you need in order to create a good model? So we'll talk about that later after we talk about polynomial degree and about regularization. So let's consider the question of polynomial degree. Remember the symptoms of overfitting and underfitting. Underfitting, the fit is poor on the training set as well as testing set. Overfitting, the fit is good on the training set but poor on the testing set. Now, testing set is the final determination of our performance of the model. So what we want is a preliminary determination of the performance before we get to the testing set to see if the training fit really is too good and we are possibly using a model with too high polynomial degree. The way to make this preliminary determination is to use cross-validation. Now, we talked about this earlier during linear regression, so I think it's useful to go back and review that discussion briefly to put things in proper perspective. Okay, so we had this slide before where you take all of your available data and divide it into train plus cross-validation and test. As we know, testing gives me the final indication of the accuracy. Now, this picture does not mean there's a fixed CV portion and a fixed train portion. What it means is that this data can be considered as train plus CV, and we'll see how that works in a moment. I also want to point out here that there's two types of cross-validation mentioned here: k-fold cross-validation and leave out one cross-validation. And here we're just talking about k-fold cross-validation. Leave out one cross-validation would simply mean that you take all your training data except for one data item and train on all the data except for that one and then predict the one. And you do that for every single item in your training set. So that means you would train a number of models equal to the size of your training set. And from those results, you can get an estimate of the accuracy of your model with error bars. This is also called jackknife. I won't go into that in more detail. We'll look instead at the k-fold cross-validation case. All right, so we have training plus cross-validation. So you treat them first as one big training set, and you train your model. Then you divide into folds. So these folds are going to be used one by one as cross-validators, in the sense that first you train a model on these three, and then you test it on the fourth set. So that's one number that will give you one accuracy number. Then you train on these three folds and get an accuracy number on this fold. That gives you another accuracy number, either precision or accuracy or MAE or MSE or some measure of how well your model is doing, right? You do the same for this. Train on these three sets, take that as your training set, and then use this CV basically as a preliminary testing set. So this same thing here, you have used this one as preliminary testing set. So you have done 4 preliminary tests. You've tested on 4 preliminary sets, and you're going to get 4 evaluations of your model. As I said, it could be either the mean squared error, or it could be the precision or accuracy or F1 score. And so what that gives you is a number, an evaluation plus a kind of error bar, because you have more than one number. Right? If you just have one number, you're not really sure how accurate that number is. But if you do it 4 times like this, you have a spread of numbers, and that will give you some idea of how good your model is. Now, I will point out that the model that you're getting from training, just from using just part of your training set, is not going to be as good as a model that uses all of the training data, because typically it is true, more data means a better result. However, this does give you some estimate, and in fact, this would be an underestimate of the precision or F1 score, whatever score you're going to use. And it's better to be conservative rather than to be too optimistic. All right, just to recap, first you treat as one big training set, you train your model. Then you divide into folds, for instance, 4 folds. However many folds you use, there's really not a fixed specification. 4 or 5 are common. It does depend on how much data you have. So you train k times. Each time you take one of the folds as your, quote, testing set, and the others as training. Then to get a performance estimate, you average over the k different estimates that you have. Now here it says arguably like stretching out your data 4 times larger. That's kind of, well, you don't get something for nothing. But you do get 4 numbers, which I said gives you some average, some estimate rather of the variability of your estimate. So the key here is that this is a way of comparing different models. You compare the different models before you apply them to the test set. So you can do cross-validation for different polynomial models and use those results to choose a polynomial model that has the right balance between underfit and overfit. So how does that work? So we take several different polynomial models of different degrees. So here we're just looking at the case of one feature. Now you could use several features. Okay. So you do a hypothesis for each degree, right? So this is a linear model, quadratic model, etc. Now for each of these models, we can find the best theta by training on the entire training set. That doesn't tell us which model is the best. It does give us a cost for each model, which we'll call J-train, because it's the cost derived from the model on the testing set. Now we also apply cross-validation to each model, and we'll get a cross-validation cost, which you remember will be the average cost of the different cross-validation instances. Now you plot these values on a graph, and you pick the model that has the lowest J cross-validation. Then your final estimate of the accuracy of the model will be when you apply the model to J-test. All right? So this step here, the J cross-validation, is going to enable me to choose the model with the best polynomial degree. So just to recap that process, for d equals 1, you minimize J on the testing set, and that will give you your theta 1 parameters. That will give you, you'll have a J train, that is the J for the entire training set, and you'll have a J cross-validation, which is the average of 4 cost functions. That is, if your cross-validation includes 4 folds. Same with d equals 2, same with every single d. All right, so you're getting J-train, JCV, and as I said before, JCV is going to be an average of 4 numbers. J-train is a single number derived from the model on the entire training set. Now when you plot these, it should happen that the JCV goes down as the underfitting decreases, and then it goes back up again as overfitting increases. So there should be a minimum value. Assuming that d equals 2 is the minimum value, then that's the model that we choose. We apply that model to the testing set, and we get our cost function that gives us our performance. So you should expect curves like this. right? So the training error should go down as you increase the polynomial degree, and that's because you're getting better and better fits when you're using all the training data and you're fitting one model. However, the cross-validation score should start going up again when you start overfitting. Because you're really doing a preliminary test, the cross-validation set is not associated with the set you're training your model on, and the model that overfits is going to perform poorly, right? So the sweet spot is here, and you're going to choose this degree for your model. And you see on this side, you're getting underfitting, so you get bias. On this side, you're getting overfitting, and your training is good, but when you test it out using cross-validation, it's not so good, right? Okay, so that's our discussion on polynomial degree. Next video, we'll talk about how much to regularize.